have discussed various aspects of cache organization. In today's lecture, I will give some illustration about how cache accesses are done, and also we will look into some of numerical problems pertaining to cache performance. So, this illustration would be essentially like simulation. So, we will take small example and try to see the effect of various changes in the cache organization. For example, what happens when you change the block size, what happens when you change the associativity. So, in a small example, we will look at some sample references to memory addresses and see how you get a hit or a miss. And at the individual access level, you will be able to see when a miss gets converted to a hit or hit gets converted to a miss by making a change in the organization. So, this is one way of looking at cache. What is typically done is that you look at it grossly in a statistical sense, which gives an overall behavior, but this detailed view, detailed illustration is meant to see the exact mechanism which works behind cache accesses, misses and hits. So, then we will spend a little bit of time on trying to see what is the overhead in a cache organization in terms of the extra bits you require for holding the tags, and what are the factors on which it depends, that we will see. Then couple of numerical example about cache performance in different contexts we will see. So, here is a small cache which we will use for demo. So, this is a direct map cache with 16 words. So, we are not worrying about bytes and words, let us assume that everything is words. So, you will get address sequence from memory or from processor trying to access the memory, and each access would be examined. We will see whether it is a hit or a miss depending upon what the status we see on the board. So, this is these are 16 words of the cache numbered from 0 to 15, and the addresses which we encounter. So, there is some sequence of address which is stored in this demonstration, which will come out, and we will record hit and miss. Also, we will keep track of the total number of accesses made and total number of hits encountered and misses encountered. So, to begin with, we are assuming that it is a direct mapped cache, right. So, the feature of this kind of cache is that given an address of memory, the location in the cache is fixed. Okay. So, if cache size is 16, given the memory address, you could say address modulo 16, and you will see where it is going to fit. So, we will not worry about the memory contents, but what we will keep record is essentially which word of memory is sitting in which location. Okay. So, you can see that first address which came was address 1, and naturally it is supposed to sit here. The cache was empty initially, and therefore, we record this as a miss. So, here is the place where I am going to record the addresses, and it will record the misses and hits here. So, first one is a miss, and obviously, initially we are going to encounter a lot of misses, and it is only when you come to reuse of some address, when addresses start repeating, then there is some possibility of having hits. So, initially there will be mostly misses. Let us proceed further. Four sits in this position, 8 sits in that position. So, just for space I have split the whole thing into 2 columns, but assume that it is a single one dimensional array. So, you have addresses 0 to 15, and initially numbers are sitting in their natural places. Okay. Now, you see what happened. Address 20, which you take modulo 16, is same as 4. Okay. So, 4 has been replaced, 4 has been thrown off, and if there is occurrence of 4 again, although we would have brought this to cache, we will not be able to find it next time. And 17 comes and replaces 1. So, here is these are the spots where you can see that perhaps a different cache organization could have helped, right. 19 comes in position 3, 56 replaces 8, okay, because 56 modulo 16 is 8, 9, 11, 43. So, 43 replaces 11. Oh, I am sorry, I think it skipped, went through couple of steps quickly. So, 4 came again, and that time it was a miss. We can actually, let me come to that point again quickly. So, 20 replaced 4, I think 4 comes at this point. Yeah. So, 4 throws 20 back again. Imagine if your program behavior was like this, that 4 and 20 were being accessed repeatedly, then they will keep on fighting with each other. So, fortunately 5 which was loaded initially in the fourth cycle is still there, and so you get a hit here. Six, 9, 9 is already there. So, 9 is another hit, and then 17 is again a hit, because 17 is already there. So, the overall tally is that there were 16 accesses which were made, only 3 are hit, 13 are misses. Now, what do we expect if we make changes? When suppose we change the block size, we increase the block size, what block size will try to help you with is spatial locality. It will capture spatial locality, that if you are having references which are close to each other in address, in those areas you are likely to have additional hits. Okay. So, the next one we look into this, but we are going to continue with direct mapping. So, it may not help perhaps in the areas where some data was brought in and it was thrown because of clash. Okay. So, next scenario is same direct map cache with block size equal to 4, right. I have just split the cache into 4 blocks, 0, 1, 2, 3, these form one block, 4, 5, 6, 7 form another block, and so on. So, now the meaning of this arrangement is that when you make an access, you are looking at the block level. Tags are actually stored, although I will show all the locations filled up, but tags are stored 1 per block, and when you find a miss, you are getting the entire block from the main memory and filling up in the cache. Okay. So, first time when address 1 was encountered, there was a miss, but whole block got filled up 0, 1, 2 and 3. Okay. Then address 4 was encountered and second block got filled. Okay. You now its advantage would be seen if addresses within the block get referred again. So, 8 fills in another block, and now since there is a reference to 5, there is a hit because of that, right. So, here you can see some advantage of a larger block size. 20 replaces this block. So, that problem continues. Okay. 4 was replaced by 20. Now, the entire block 5 is also replaced. 17 replaces 1, but 19 gives you a hit, because 19 is in the same block as 17. 56 replaces 8. Again, since you are referring to 9, that block beginning with 56 is thrown out again. So, here is a miss again. 11 is a hit, because we had referred to 9 and that block is there. So, access to 4 is also a miss here. The block beginning with 8 is again replaced. 5 is a hit, because by virtue of 4 which was accessed. 6 is also hit, 9 is a miss, and 17 is a hit. So, on the whole there are 3 additional hits here, and the total performance is improved. We can see which are the new hits which have come. It's not scrolling. So, earlier we had hit for the last 5, 9 and 17. Uh, 9 we have lost, okay. 5 and 17 are still there. The additional ones have come here, here, here and here. At these 4 positions you have additional hits. So, it is not that whatever is a hit remains a hit, okay, because the total number of blocks is reduced. So, you can see some effect of increasing the block size too much. So, some of the hits may be lost, whereas others may be added, and one has to see it carefully. If you recall, I had shown you a variation of miss rate by versus the block size. So, initially the miss rate decreases, okay. So, that is improvement in performance, but if you increase the block size too much, you start losing, and miss rate may increase again. Okay. Now, let us look at associativity, which gives you flexibility of placing blocks at more than one locations, and here one has to decide what is the replacement policy, because each block can be placed at more than one location. When it comes to replacing an old block, you need to see which one needs to be replaced. So, in this example we will follow LRU policy. Okay. So, the block which is least recently used will get replaced whenever there is a need. So, what I have done is I have repeated those addresses 0 to 7 here. Effectively each row, for example, this 3 and this 3, they form a set. So, any I will take the addresses now modulo 8, okay. Whatever address comes, you take it modulo 8 and try to place it in a particular row. So, for example, if address modulo 8 is 3, I will see if this is free or that is free. It can be placed in one of these. If both are filled up, both are occupied, then one has to be replaced, and that will be done by LRU policy. So, there are 8 sets and there is a degree of associativity which is 2. Okay, block size is still 1, right. So, initially everything is empty, I place this 1 here, next is 4 gets placed there, then 8 is placed at this location 0, okay. 8 was the location for 8 was this earlier. but now of course both are location 0. 5 comes here, 20 does not throw 4 away now. So, this is a change which you must observe. 20 can be placed here, 20 modulo 8 is 4 and there is a vacancy in this set. So, 20 can be placed here. 17 does not throw away 1, it has another place. 19 comes here, 56 again does not replace 8, 9 has replaced 1, okay, because now we were falling short of space here, and out of 1 and 17 which one should have been replaced, that you can see. So, you either have to replace 17 or 1, but this is more recently used, that is less recently used. So, 1 gets replaced. 11, 4 again. So, 4 was not thrown. So, here is a new hit we have got. 43, 5, 5 is again a hit as was the case earlier, 6, 9 and 17. So, if you compare it with the first case, okay, we have a marginal improvement, and the new hit which you can see has come up here, right. Okay. Now, let us extend the degree of associativity further, let us make it 4-way set associative. So, the 16 block cache, 16 word cache is divided into 4 sets, each with having 4 locations. So, we will do it in similar manner. Notice that the sequence of addresses we are following is same, so that we have a fair comparison, and in this, if I remember correctly, nothing will be thrown away, there is enough room for everything. So, 4 is a hit, 5 is a hit, 6 is a miss, 9 is a hit and 17 is a hit. So, so we still capture same number of hits, okay, and what one could say is that this is a kind of saturation point as far as this scenario is concerned. By increasing the degree further, we are not really going to get anything better. Okay. So, now after having gone through this exercise, we would like to look at different types of misses. Okay. There are 3 types of misses. One is compulsory misses. Compulsory misses are those which you encounter initially. Initially, when you are starting with empty cache, there are compulsorily some misses, because nothing is there in the cache. So, first time anything has to be referred to, has to be brought. Then there are capacity misses. Capacity misses are because the cache has limited capacity, it cannot hold everything which is there in the main memory. So, something has to be out, and any misses which are resulting from that limitation are categorized as capacity misses. Thirdly, we have conflict misses. Conflict misses come because of a specific mapping approach which you have, and more the degree of associativity you have, less are the conflict misses. So, conflicts are because many main memory locations contend for same position in the cache. and one word comes and throws something else. So, now if you look at previous examples, okay, let us start with this one. Which of the misses are compulsory misses and which are not? Yeah, there are lots of compulsory misses. Let us find out which misses are not compulsory misses. Wherever we are making second reference, okay, that is either due to conflict or limited capacity. So, for example, second reference to this miss is not a compulsory miss, because it was something which could have been saved, okay, and I suppose everything else. No, this 5 is a hit. Okay, so this is not a miss. This is the one which is not compulsory. Everything else is fine. Everything else is a compulsory miss. Okay, in the next one, you notice that compulsory misses have been reduced here. Okay, and what has reduced? It is the larger block size which has reduced compulsory misses. So, 5 for example, which is compulsory miss, is no longer a miss at all. But we have lost 9. So, what kind of miss is that? This is not a compulsory miss. Okay, now here is a little bit of problem, whether you call it capacity miss or conflict miss. Between capacity miss and conflict miss, it is hard to pinpoint for individual miss whether it is conflict or capacity. So, this notion is actually at a statistical level. You look at the overall miss rate. So, let us say 1% misses are there, 99% hits are there. So, that one could be broken up into, let us say 0.4 could be compulsory misses, 0.3 could be capacity misses, 0.3 could be conflict misses. So, the way you precisely define capacity misses is that you take fully associative cache, which means there are no conflict misses. Okay. So, whatever you are getting over and above compulsory misses is capacity misses. So, fully associative cache has only compulsory misses and capacity misses. In a cache which is not fully associative, the additional misses you get at in terms of average, in terms of the total gross behavior, they are the conflict misses, because they can be attributed to conflict. Otherwise, individually it is a bit of problem to categorize a miss as a capacity miss or a conflict miss. All right. Now, let us move to the issue of sizes and bits. You have cache of certain size, certain organization. How many bits you have to incur as overheads for storing the tags? Okay, it depends upon various parameters. For example, suppose the memory address space is addressed by k bit addresses. Okay, so in MIPS, for example, this will be 32, and suppose cache size is s bytes. Now, we are assuming that cache is or the memory is byte addressable, and let s be the size of the cache in bytes. Let b be the size of block. So, it is b bytes. B can also be, b would typically be some power of 2, and let a denote the degree of associativity. Okay. So, a equal to 1 means it is direct mapping cache, and when a gets its maximum value, then it is fully associative. So, how many sets you have? S is the total cache size and B is the block size. So, S upon B actually gives you the number of blocks. Okay. You divide that by A, you get the number of sets. Okay. So, in a two-way set associative, the total number of sets is half the number of blocks and so on. How many bits you require to index, because the address is divided into tag part, index part, and then there is an offset within the block to access a byte or a word within a block. So, number of bits required to access one set is naturally log of this, okay. And number of bits required to address a byte within a block is log of B. So, the address which is of k bits, if you subtract the number of index bits and number of bits required to address a byte, the remaining are the tag bits. Okay. So, k minus log of S by A B minus log of B, which you can write as k minus log of S upon A, because this B will cancel with that B. So, these many bits are required to define each tag, and you can see that as A increases, the tag size will increase, right. The total number of tag bits equal to the tag size multiplied by the number of tags, and number of tags equal to the number of blocks, which we said was S upon B. So, this way you can actually calculate the overhead of cache in terms of the tag bits. So, actually all these tags together are called what is called a tag, the cache directory. So, cache has two parts, cache directory and the cache data. Okay, now let us take some numerical example and try to relate various performance parameters to each other. We have seen that effective CPI in presence of a cache is the CPI, assuming that there were no cache misses, it was ideal situation, plus the additional cycles which are coming because of misses. So, these are stall cycles, they depend upon the miss rate, miss penalty, that means additional cycles encountered, additional stall cycle encountered per miss. Okay. And the third factor is number of memory access per instruction. So, the product of this gives you the total number of stall cycles per instruction. So, suppose in a given case we have the basic CPI as 1.2, right. Miss rate is 0.5% and block size is 16 word. How do you find the miss penalty? So, we would need to we will need to find miss penalty to get this. So, how do we find miss penalty? That will come to in a moment. For this example, we assume that number of memory access per instruction is 1. The miss penalty will depend upon what kind of memory cache interface you have, and we have talked of 3 interfaces if you recall. In one case we have memory which is one word wide and you access one word at a time, transfer one word at a time. Second case was that you have memory which is multiple word wide and multiple words can flow on the bus simultaneously. Lastly, we have interleaved memory or a page DRAM. So, suppose it takes one cycle to transfer either data or address over the bus, right. So, effectively assuming that bus cycle is same as the CPU cycle. Assume that memory latency is 10 cycle, that means once address is given, memory has a delay of 10 cycles. After 10 cycle it will respond with the data. So, given this we can find out miss penalty for case A, where one word is accessed at any time. So, for each word you spend 1 cycle sending the address, 10 cycle taken by the memory, 1 cycle again by the bus to send the data back. So, total 12 cycles, and for a 16 word block this process will be repeated 16 times and total of miss penalty is 192. In case B, let us assume that the memory is 4 word wide and the bus is also 4 word wide. So, that means this cycle of 1, 10 and 1, this needs to be repeated only 4 times, and therefore, we encounter 48 cycles. In the last case, suppose we assume that there is 4-way interleaving, but the bus is 1 word wide. That means, we will in one transaction will send address, take 1 cycle, then memory takes 10 cycles. Actually, there are 4 modules, each one will be ready with its data and 4 cycles will be required to send it back to the CPU. So, total of 15 cycles are required to get 4 words, and that is repeated 4 times to get a block of 16 words. So, that gives you a total miss penalty of 60. Okay. So, we will get 3 different answers for CPI for these 3 cases. So, coming back to CPI calculation, we had effective CPI as 1.2 into 0.5% was the miss rate. So, we put that as a fraction here. Miss penalty we have just calculated, we will substitute the values, and number of memory accesses per instruction is 1. So, putting the value of 192 as miss penalty, we get CPI effective as 2.16. In the second case, miss penalty is 48, CPI comes out as 1.44. Third case, miss penalty is 60, CPI comes as 1.5. Okay. So, you would notice that if you look at miss penalty, there is so much variation, but the factor by which performance varies on the whole is not the same. Okay. So, it is a variation from, let us say 1.44 to 2.16 as you change the miss penalty from 48 to 192. So, ultimately in terms of CPI, this is what matters. All right. Now, take another example where we try to do comparison of different architectures. So, suppose we have 3 different caches with different organizations. First 2 are direct mapped cache, and then the third one is set associative cache with 2-way associative access. The block size is 1 word in the first case and 4 word in the second and third cases. Here we are given instruction misses and data misses separately. So, that means out of 100 instructions we try to access, 4 times we get misses, and in the first case. Similarly, we make 100 accesses to the data and there are 8 misses. So, we are given CPI for the first case, we need to find CPI for the remaining cases. Miss penalty, as we know, depends upon the block size. So, without going into details, let us say that miss penalty is given by 6 plus block size. This is in terms of number of cycles. Also, we need information about how many instructions make reference to data. So, each instruction makes one reference for fetching the instruction itself, and here 50% of the instructions make data reference. So, they are either load or store. So, now we can calculate the number of stall cycles. This is the miss penalty. In the first case, since the block size is 1 word, this is 7 multiplied by the miss rate. So, for instruction it is 0.04, for data it is 0.08, but only half the instructions make data access. So, multiply by half here. So, what this says is that in cache 1, on the average there are 0.56 stall cycles per instruction. Going to cache 2, the miss penalty is 10 because block size is 4, right. I miss 0.02, D miss 0.05 as given, and half, because half the instructions refer to data, we have a factor of half here, and this comes out to be 0.45. In the third case again similar, but this factor is reduced. So these are the extra values which have to be added over basic CPI to get the overall CPI. What we are given here is effective CPI 2.0. Okay. So basic CPI can be obtained by looking at this. Out of 2.0, 0.56 is because of stalls, cache stalls, and the rest is the basic CPI. So which can be assumed to be same for these cases. So CPI for 3 cases, it is 2.0 here. For the second case 2.0 minus 0.56 plus 0.45, and similarly for the third one. So the figure we are getting is 1.89 and 1.84. Now this is all in terms of number of cycles, but as you know we need to take into account the clock cycle, clock period also, and typically more the complex structure you have, like you have associative cache, the cycle time is likely to be larger because the hardware has to allow multiple comparison at the same time. So it may be slower and it may pull down the clock period. So the figure may be a little exaggerated here, but assume that for direct mapped caches clock period is 2 nanoseconds, and for the set associative case it is 2.4 nanoseconds. So if you multiply the CPI figure with this figure, you will get the time spent per instruction. Okay. And this is the overall indicator of the performance, take into account all the aspects. So looking at that, it is the second one which seems to be the best. Of course, if the increase here, this increase was not so much, possibly this could have done better. Okay. So we have to see that by making it associative, by what amount is this miss getting reduced. So sorry, it's running away. If the advantage you are gaining here is not substantial, it may be lost by the negative effect you will have on the clock period. So that has to be kept in mind. Okay, now this example looks at multi-level cache. So suppose you have 2-level caches. What we will do is first we will analyze situation with one cache and see what improvement the second cache brings to the overall performance. So suppose we have a processor with a CPI of 1 when there is no miss, and it is running at clock of 500 megahertz. The main memory access time is 200 nanoseconds, and the miss rate is 5%. So if suppose there was only a single cache, we are saying that the miss rate is 5%. It is observed that by adding L2 cache, second level cache, there is a reduction in the miss rate. So now suppose the miss rate becomes 2% only, it drops from 5 to 2. What is the performance improvement? What is the net effect on the CPI? So we need access time data about the L2 cache, and suppose that is 20 nanoseconds, main memory is 200 nanoseconds and L2 is 20 nanoseconds. So and the access time of L1 cache is subsumed in this. Okay, this is when there are no misses. So miss penalty when one has to access memory is 200 nanoseconds. To convert this into cycles, we divide it by time period of this, which is 2 nanoseconds. So 200 by 2 or 100 cycle is the miss penalty for making access to main memory. Okay, we are not going into details of how we get this, because ultimately it depends upon the bus architecture, block size and so on, but whatever all that is, the net result is, let us say, 200 nanoseconds. So if you have just L1 cache, then what is your effective CPI? it is 1, which is this figure, plus 5%, that is a miss rate, into 100 cycle, which is a penalty. So, this comes out to be 6, right. Once again we have made an assumption here that number of memory accesses per instruction is 1, right. There are no data accesses, or everything is just 1. Suppose you introduce L2, the miss penalty of L2 itself is 20 nanoseconds divided by 2 nanoseconds, which means 10 cycles. So, now the total CPI, taking into account misses at various levels, will be the base CPI plus stalls due to misses at L1 level. Okay. So, when there is a miss at L1, you make access to L2. So, there are some stall cycles encountered. If you have miss at L2 level also, there are some additional cycles you incur. So, this will have to be 10 multiplied by the miss rate here. This is 5, this is 100 multiplied by the miss rate here. So, 1.0 the base CPI, 5% miss at L1 level multiplied by 10, which is the miss penalty, and there is also multiplied by 1, we assume that 1 memory reference per instruction, otherwise that factor will come here, plus 2% is the miss at L2 level multiplied by 100. Okay. So, now this first term gives us 0.5, second term gives us 2.0, and the total is 3.5. So, what is the ratio? By what factor has performance improved? You can simply divide CPI, which we had earlier 6.0, and the CPI you got now 3.5, so 1.7. So, now let me clarify certain terminology here. We are saying that when you put L2, there is a 2% miss on the whole. Okay. So, this is what is called in a multi-level cache terminology, this 2% will be considered as global miss, that is all caches put together, that as a system is taking care of 98% of the accesses, and it is leaving out only 2. But if you were to focus your attention on L2 cache only, L2 is receiving some accesses, it is receiving some requests, some of them it is able to serve, some it is losing. So, there is something called local miss for L2, okay, that is not shown up explicitly here, right. There is also a term called solo miss. Solo miss is the term, suppose now in this 2 level cache system you remove L1 and L2 is the only one left, then the misses which you will see at that time are called the solo miss of L2. Solo means when L2 is alone. So, is there some relation between these? In a specific case, there is a very nice relationship between these. When you have completely the data in L2 is all inclusive of data in L1. Okay. So, if you have the situation that anything which is there in L1 is there in L2, but L2 has something more, because L2 will be typically of larger size than, much larger size than L1. This property is called inclusion property. It may hold, it may not hold. Okay. We will come to the point why it may not hold, but suppose it holds, then the solo miss of L2 will turn out to be same as the global miss which we are seeing here. Okay. What it means that if L1 L2 together are showing you a 2% miss, having put L2 alone would also have shown you 2% miss. Then what purpose L1 is serving? L1 is reducing the time, because L1 is taking care of some request and reducing the penalty you are incurring. Okay, and also you can relate now the global miss also to the local miss. So, okay, you can look upon it like this, that suppose 100 requests are made by the processor 95 are taken care by L1. Okay. Only 5 are going to L2. Out of those 5, effectively L2 is taking care of 3 and losing out on 2. So what is the local miss of L2? Local miss is 40%, right? Local miss is 40%. So it looks a very large figure, but it is because only selected requests are coming to L2 and it is able to serve some of those, and even by doing that it is reducing the overall miss rate. Now, coming back to the inclusion property, the inclusion property may not necessarily hold. Why? Because it may happen that L1 may retain some data which L2 throws off for its own, because of its own structure and replacement policy. So, L1 and L2 could be structured totally independently. The degree of associativity could be different, the block size would typically be same, but degree of associativity is typically different, and other policies like write through, write back, they could also be different. So there is a possibility that something which was brought to L1, maybe at that time it was there in L2, but eventually by the time you have second reference to that, L2 has meanwhile thrown it. So those situations could arise and inclusion property may not necessarily hold. Okay, so let us conclude by summarizing what we have seen today. We tried to simulate cache for a few simple situations. An idea was to focus attention on individual hits and misses to see which factor is affecting what. Okay. Then we moved on to quantify the storage overheads in a cache organization, counted the tag bits and the number of tags and so on. Finally, we took some numerical example to get a better insight into what factors influence the performance in a statistical sense, in a gross sense. What are the miss rates, how do they affect the miss penalty, stall cycles, not miss penalty, stall cycle, and how they ultimately affect the CPI. We have seen that what are the variations in these parameters due to changes in the cache organization, and as you go from one level to two level, how things change. I will stop at that. Thank you.